Alrighty, my students, so here is the second video. It is 1:30 p.m. And good afternoon. So now we're going to be solving a free response question. This was from, I believe, the 2016 AP exam. This is considered one of the long free response questions. Excuse me, I want you guys to hear my phone whenever it goes off. Yeah, so this is one of the longer free response questions. I did cut off part of it because I didn't want this to be too long. But the main ones I wanted to focus on were letters A through C because it focuses more on intermolecular forces, which is the topic we are covering. Okay, so let's get started. So this is from the free response section. So it says the structures of two compounds commonly found in food, lauric acid, which is here on top, and sucrose, which is your typical table sugar, posted here on the bottom, are shown above. So part A says, which compound, lauric acid or sucrose, is more soluble in water? Okay, so when reading this question, you see that it's more soluble in water. The first thing that you should have recalled is, again, a little thing we covered in the previous video, like dissolves like. So it's asking which of the two is considered to be more polar. Okay, so that's what we're going to be looking at. Then it says justify your answer in terms of the intermolecular forces present between water and each of the compounds, excuse me. Okay, so let's look at what intermolecular forces are present. So So in lauric acid, the first thing that you guys should notice is the presence of these two oxygens there. Okay, so those two oxygens, or this OH group here, that OH group will most likely be able to hydrogen bond with other lauric acid molecules around it. Okay, so then we look at the structure for sucrose. Okay, so in sucrose, we have a lot more of those OHs, which are possible sites for hydrogen bonding with other sucrose molecules. Okay, so with those OH groups, there is a dipole formed between the oxygen and hydrogen. So that means you are going to have a partial negative on the oxygen, partial positives here. Oxygen is more electronegative. So these are going to interact with other hydrogen, other oxygens in the other lauric acid molecules. And the same thing happens here in sucrose. However, in lauric acid, we only have one site for hydrogen bonding, and in sucrose, we have all of these. So the one that is more polar and more open to hydrogen bonding is going to be sucrose. So that means sucrose is more soluble in water. Okay, so now let's put that in writing. Okay, so this is for number 3, letter A. My handwriting might be a little bit ugly here, my students, so I am sorry. I can't write as neatly with an Apple Pencil as with a regular pencil. Okay, so first we need to identify what is our correct answer. So sucrose is more soluble than lauric acid. Okay, so that is my answer. Now I need to justify that. Okay, so we said stronger interactions. Stronger interactions occur between sucrose and water molecules due to a greater capacity due to a greater capacity for hydrogen bonding. Bonding as a result of a larger number Whenever you're writing out your answers, my students, please write the full word. So for between a number, I'm just doing it as a shorthand right now. Due to a larger number of OH hydroxide groups in sucrose. Period. Okay, sucrose is more soluble than lauric acid. Stronger interactions occur between sucrose and water molecules due to a greater capacity for hydrogen bonding as a result of a larger number of hydroxide or OH groups in sucrose. Okay, and there you go. So if you want to elaborate, I can give you the full answer according to College Board past AP exams. So then you want to elaborate a little bit more. Although lauric acid has one site for hydrogen bonding, comma, the long hydrocarbon chain causes LDF, London dispersion forces, to be predominant, to be the predominant or main interaction with water molecules. Period. Okay, so there you go. I know here it looks like a lot of writing. It's really only 3 sentences, but I have to write big here on the iPad. Okay, so there is your answer for letter A. Okay, so let's go on to letter B. Letter B does involve some slight calculations. Okay. So letter B, it says, assume that a 1.5 gram sample of lauric acid is combusted and all of the heat energy release is transferred to a 325 gram sample of water initially at 25 degrees Celsius. Calculate the final temperature of the water if delta H of combustion of lauric acid is negative 37 kilojoules per gram and the specific heat of water is 4.18 joules per gram Kelvin. Okay, so this is a topic that we have covered previously. Okay, I think I have enough space where I can solve it underneath. So for this one, you are going to be using our handy dandy for letter B. Q equals ms delta T or mc delta T, regardless the MSAT or the MCAT equation. Okay, so we are given all of the necessary information. So we're going to see, it's asking calculate the final temperature of the water or the change in temperature. Okay, so we're going to be solving for our delta T. So the Q in this case is the delta H of combustion. So Q is equal to your, let me see. Oh, excuse me. Okay. So to calculate Q, we need a C first. It says delta H of combustion is 37 kilojoules per gram, but we did not just have 1 gram of lauric acid. We had a 1.5 gram sample. So to find our Q, to find out how much energy is released, we're going to multiply, and we know it's released due to the negative sign there. So we're going to multiply 37 kilojoules per gram times 1.5 grams. Okay, so let's do 37 times 1.5, 55.5. So we can round that up to two significant figures, right? Because they're both two significant figures. So 55.5, we round it up. That is 56 kilojoules. Okay. However, since the specific heat of water is given to us in joules, we're going to want to convert this kilojoules to joules. So 56 kilojoules times 1,000 times 1,000 joules and 1 kilojoule means this is equal to 56,000 joules, and that is equal to my Q in this case. Okay, so we have our Q, which is 56,000. Our M is our mass of water, which we have, which is 325 grams. That's my M. Okay, S is my specific heat of water, again, which is given to me at 4.18. So I'm going to be looking for the change in temperature. Okay, so then if I rearrange this, I want to get delta T by itself, divide both sides by MS. My delta T, my change in temperature, is equal to my Q divided by my M times S, right? Okay, so I'm going to erase this over here. So we can plug in what we know. So my Q, we said, is equal to 56,000 joules divided by the mass of water, which is 325 grams, times the specific heat of water, which is 4.18 joules per gram Kelvin. Okay, so then let's solve this. So 56,000 divided by 325 times 4.18. So I'm going to do this a little bit differently since I only have this calculator. But 56,000 divided by 325 divided by 4.18. Okay, so my change in temperature is 41 degrees. Oof. Let's make sure that. Okay. Is equal to 41. Okay, so then we're going to add this 41 to the initial temperature of 25. So to find my final temperature, I'm going to take my initial temperature, which is 25 degrees Celsius, plus the change, which is 41. 25 plus 41, 66. So my final temperature for letter B is equal to 66 degrees Celsius. Okay. So that's it for number 3, letter B. So let's go on to part C. It says, in an attempt to determine the delta H of combustion of lauric acid experimentally, a student places a 1.5 gram sample of lauric acid in a ceramic dish underneath a can of aluminum containing 325 grams of water at 25 degrees Celsius. The water ignites the sample of lauric acid with a match and records the highest temperature. Okay. The student ignites the sample of lauric acid with a match and records the highest temperature reached by the water in the can. Okay, so let's draw this out. My drawings are notoriously not great, but we'll still draw this out. Okay. So then we have a can made of aluminum. So an aluminum can, right? And it contains 325 grams of water. So inside my aluminum can, I have 325 grams of H2O, okay, at 25 degrees Celsius. Okay, the student ignites the sample of lauric acid. So underneath here, I have a sample of lauric acid, and it says it's a 1.5 gram sample of lauric acid, and then the student will ignite it. Okay, that's my fire. We'll ignite it. The heat will be transferred to the aluminum can, to the water, and it's going to see, the student is going to measure how much the temperature of the water increased. Okay, so that's the experiment the student is doing to see if he could experimentally calculate the heat of combustion of the lauric acid. Okay, so part 1 says, the experiment is repeated using a can of the same mass, but this time the can is made of copper. Okay, so let's just redraw that quickly. So instead of a aluminum can, it is made of copper. We have the same thing with water, with our 1.5 grams of lauric acid underneath, and it is ignited. So our temperature of the water is going to increase. Okay. The specific heat of copper is 0.39 joules per gram Kelvin. 0.39 joules per gram Kelvin. And the specific heat of aluminum is 0.90 joules per gram Kelvin. Excuse me. So it's asking, will the final temperature of the water in the can made of copper be greater than, less than, or equal to the final temperature of the water in the can made of aluminum? Okay, so here they're testing your knowledge of if you understand what specific heat is measuring. So specific heat is the value needed to raise 1 gram of a substance by 1 degree Celsius. The amount of energy required to increase the temperature of 1 gram of a substance by 1 degree Celsius. So the higher your specific heat, the more energy is required to change that temperature. Water has a very high specific heat, which is why it takes forever for water to boil on your stove whenever you're trying to make anything. So in this case, we have aluminum with a specific heat of 0.90 and copper with a specific heat of 0.39. So since copper has a much lower specific heat, it requires less energy to increase the temperature. So one would expect the water in the can of copper to have a higher final temperature than in the can made of aluminum, because aluminum has a higher specific heat. Aluminum's higher specific heat means it requires more energy to change the temperature of it, which means it's acting as a little bit of an insulator and prevents the change in temperature for the water. Okay, so then let's answer that on the next page. Okay, so this is number 3, letter C, part 1. Okay, so the temperature will be greater in the can made of copper, Cu. Okay, and why? So that's our answer. Now we need to justify it. Since copper has a lower specific heat, Since copper has a lower specific heat than aluminum, more heat will be absorbed by the water oh, hold on, excuse me, my eyes itching, in the copper can than the water in the aluminum can. Okay, so it says the temperature will be greater in the can made of copper, so that is my correct answer. And then I need to provide a proper justification. So it says since copper has a lower specific heat than aluminum, more heat will be absorbed by the water in the copper can than the water in the aluminum can. Okay, so that's my answer for letter C. So let's go, or letter C part 1. So now let's go and look at part 2 here. Okay. Oh, excuse me. My eye's bothering me. It says, in both experiments, it was observed that the measured final temperature of the water was less than the final temperature calculated in part B. Identify one source of experimental error that might account for this discrepancy and explain why the error, it's a weird word, would make the measured final temperature of the water lower than predicted. Okay, so there's a couple different answers for this one. So when doing the experiment, maybe, in this case, let me just redraw it. Shouldn't have erased it. Maybe I can, there we go. Okay, so in this case, in this experiment, there are a couple of things that could have gone wrong due to human error. Okay, so maybe one of the possible sources of error could be that some heat was lost to the environment, right? So this isn't going to be a perfect experiment, so maybe some heat escaped during the combustion, maybe some heat left here and didn't 100% enter the aluminum can and the water, or same thing here. Okay, so that could be one of the sources of error here. One of the mistakes is some heat is lost to the environment, which would result in the temperature being a little bit lower or less than it calculated, because some heat maybe dissipated, lost to the environment, and wasn't able to be transferred to the water. Okay, so that's one possible source of error. I'll write it here. Okay, heat lost to environment. Okay, that could result in having a lower temperature. Okay, part 2. Another possible source of error could be that some heat was, instead of transferred 100% to the water, since we're using aluminum and copper cans, it could be that some of the heat was transferred to the can, or even heat was transferred to whatever thermometer you're using to measure the temperature. So heat was transferred to the can or thermometer. That could be another source. And the third possibility is during your combustion. Okay, we're assuming all 1.5 grams combusted, but maybe that's not the case. Maybe you had some lauric acid left over that didn't completely combust. So if it didn't completely combust, you're not having that perfect 1.5 grams, so that could result in a lower temperature than expected. So the other possible source of error is incomplete combustion of lauric acid. Okay, so I'm going to ask that you guys write your own response to part part 2 here. Okay, I'm not going to give you my response, but you're going to use one of these 3 possibilities, and you're going to explain why that would result in a lower or less temperature than what we calculated in part B. Okay, so that'll be it for this video. Sorry, I'm kind of going fast here at the end, but since it'll be uploaded, at least you'll be able to go back and rewind as needed. But I think that'll be it for this lecture, my students. Have a wonderful